Everybody get registered for classes this morning? Or prior to this morning, if you are an upperclassman? Okay. I am planning a quiz next week, but I want to double check when we said the third test was.
I think the third test is the following Monday.
The following Monday. Oh gosh, I was really hoping to be farther into chapter 5 by then. Okay. Yeah. So we'll do that next Wednesday. Okay. So we'll have to move quickly today. All right. I have decided to do the prepare to learn for, well, if we need to move quickly, I'm going to make that due tomorrow night. So jump right into chapter 5. So bless you. I wanted to go over a couple of stoichiometry things, and then we're going to look at gases when they move and real gases. So here's the chalk. Remember that when we are dealing with gases, we can treat volume to volume like mole to mole. So if we think about our 3 steps, if we're starting with the volume of A, in order to get to moles, we need to rearrange the ideal gas law. And so we're going to multiply that by nRT over P. And that's going to be our step 1. That's going to get us to the moles. And then our step 2 is going to be to take the answer to that and do moles of A over moles of B using the coefficients in the balanced chemical equation. That step's always the same. And then our last step to get back to volume is going to be to take pressure divided by nRT of B. And if we are doing this at constant temperature and pressure, all of this multiplication cancels out with all of that multiplication, right? And so really, we're just doing moles of A to moles of B, okay? So if we have something like this, so this is a pollutant, NO2, it's a brown gas. When you did your copper thing, that was that brown gas that came off of the copper when you treated it with nitric acid. Really toxic stuff and stuff you don't want to be breathing in. Ammonia is also a not great thing, but if you mix those two together, you end up with nitrogen gas, which makes up most of the gas in our environment, and water. So we can cancel those things out. So if I start off with, let's see, 20 liters of NH3, and I want to know how many liters of N2, then I can just use the coefficients in here. Now, I can't do this with liquids. I can't do this with solids. I can't do this with solutions. But I can say 20 liters of NH3 times, and here we can just use liters instead of moles, liters of NH3 on the bottom, liters of N2 on the top. And I would say the 5 from here and the 4 from here. And I would end up with 25 liters of N2. Okay, so not too bad there. Okay, if we are doing other kinds of stoichiometry, then we have to go through using PV equal nRT. So if our pressure is changing or if we're starting from a pressure, then we have to look at those other things. All right, let's look at a little bit of stoichiometry. So I have on the board a question about our pumpkin that we had gone in and carved the other day. You take, let me turn on the light. You take calcium carbide, CaC2, and add water, and that produces calcium hydroxide. So this is a white mess that was kind of left inside. And this molecule is called acetylene. And I balanced this equation. But this is the gas that was produced. And so what I'm interested in is if I have 0.65 grams of the calcium carbide, I want to know what is the pressure inside the pumpkin of, not of that one, of the acetylene gas. And so we'd have to know, well, what's the volume of the pumpkin? I'm going to say that pumpkin had a volume of 5.3 liters on the inside. And the temperature in the room, we'll say, was 21 degrees Celsius. Okay. So this is the stoichiometry we're going to try and solve based on what we just did. Now, this is before we lit it on fire, so it's not going to be a very high pressure. We just want to know, as it spread out within the pumpkin, what pressure was produced. So it's probably going to be a pretty small pressure because there was also oxygen in there and some water vapor and stuff like that. Okay, so if I go back to my slider here, this is going to tell me what I need to do for my different steps. So I am starting with a mass, right? We have the mass of the calcium carbide. And so that tells me I take the mass of that and do 1 over the molar weight. Mole to mole ratio is always the same. And then I'm not looking for the mass of my product. Doesn't say anything about the mass, but it says find the volume. Now on here, I have one volume that says volume of solutions, but this isn't a solution. So we're going to keep sliding. And this says volume of a gas. And this is going to look more familiar. It's going to have our temperature. It's going to have our pressure. And then slightly out of view, there's an R there. So move that over so you can see the R. There's the R. Okay. So what we're going to do is take the mass divided by the molar weight of what? Do we want the molar weight of this guy or the molar weight of our no? The no, right? And then we'll do the mole to mole ratio. And then we have the temperature, but we have to put it in Kelvin. And then we have the pressure is what this was looking for volume. Pressure works the same way, but we swap volume and pressure. Okay. Do I have pressure? It's molar weight. So we're just going to put volume down here instead of pressure. And it'll work out the same way. Okay. So our first thing then is going to be to find the molar weight of the calcium carbide. I'm going to have one of you do that. I know approximately what it is, so I'll know if you're right. You guys have that yet? 64.1. Okay. So 64.1 grams per mole. And we're going to divide, right? Didn't anticipate this ahead of time, but it looks like it's going to be pretty close to 1 mole. And all my calculators have just, they haven't disappeared. I'll just move. Now, if you want, you can just put everything in a line, but I'm going to pause partway here and figure out what our intermediate things are. So I have 0.0101 mole of calcium carbide. Now, really, I have only 0.010. I don't really get that third digit. Sometimes people will leave in their calculator the number until the end. That's essentially what you're doing if you do the whole multiplication at once. And so I'm going to leave that extra digit there just so we can kind of get halfway in between those two. So this is step 1. Step 2 is our mole to mole conversion. This one we can do in our head. What chemical is going to go on top? Oops. Yeah, no. So it's going to be this, which I'm going to call C2H2. All right. And then what numbers go in those spots? Ones and ones, because I have invisible ones there. And so this is why I said you can do this math in your head. That got canceled. So we're dealing with this chemical. So then we're going to do times R times T. What T am I going to put in? I'm going to put in 21. Going to change it to Kelvin. So 294 Kelvin. And then we're going to divide by, instead of pressure, which is on the paper, we're going to divide by the volume because those kind of rearranging the equation works out that way. So we're going to have 5.3 liters on the bottom. What'd you get? Okay. And if we only have 3 sig figs, what would you round that to? I mean, 2 sig figs. Okay. The way I plugged it in with the 101, I ended up with 0.46, but remember our last digit is where we have 0.046. That's where we have uncertainty. So if you're up or down by 1 digit on there, that's not a big deal. What are my units here? Atmospheres. So I know that because I'm looking at a pressure, right? So that makes sense. Also because kelvins cancel, moles cancel, liters cancel, and I'm left with atmospheres. Okay. Do we need to what? Yes, it's always good to have a number or unit to count, especially in stoichiometry. Okay, so let's at least set up one more. Right, so normally we're either comparing reactants or we're saying, I have a reactant, how much product do I get? Thinking about the yield. But we can do stoichiometry between any 2 chemicals. So I want to look at one where our known is a gas, okay? So this is a reaction. If you take solid sodium and you drop it in water, you're going to get hydrogen gas bubbles. It'll fizz, okay? So let's say we collect a volume of 21.2 milliliters at a pressure of let's say 601 torr and a temperature of 19.2 degrees Celsius. And we want to know what mass of sodium did we start with. So in this case, our known is the gas, and we're always start with an amount. So of these numbers, which of these is the amount of gas? What? 21.2 milliliters. So we would start our stoichiometry with that. Now, because this is using the ideal gas law, do we need to change volume and pressure? Yes. Whenever we use R, we have to use whatever units are in R. So this is going to be 0.0212 liters. And this is going to be 601 over 760 atmospheres. And then, of course, we have to change this to let's see, 273.1, 292.3. Oh. All right, so pull this down real quick. We're not going to be able to do the whole calculation. But because my known this time is the gas, that is going to be what is on the left-hand side. Okay, so I have the volume of the gas is what I start with here. Put that back into place. And then to get to moles, I do P divided by RT. Step 2 is the same. And then we're trying to find the mass of a solid. And so we're going to multiply by the molar. Okay. So we'll look at the answer to this on Friday, and then we will jump into chapter 5. Questions? Okay.